Hi students, welcome to another video on analog electronic circuits. So in this video we will have a look at frequency response of CS amplifier. This is my email IDs. I'll just go through few initial slides before we start the frequency response of CS amplifier. Of course, before we start this, so you should know the basics of MOSFET. You should be aware of how to write the AC small signal models, and you should be aware of the common source amplifier. And what you need to do during the lecture means you are supposed to have a notebook. Pens of different colors would be useful, and of course naturally you should dedicate your full time without any distractions while watching this video. To benefit most from the lecture, so set aside at least half an hour uninterrupted time. Of course you're supposed to write down everything, so that's what is WRITE. Let me just change that. So you're supposed to write everything there. Done. Okay, pause the video if you need to catch up with any of the concepts. So try to write once or twice, try to understand before you simply run through the lecture. Do the task independently. Suppose if any tasks are given in the lecture, please do it independently. Hope you are ready to begin. So I hope you have a textbook, a notebook, and you are having pens, and you have switched off your all distractions. So we'll start now with, okay, let me start this. So this is a circuit diagram of which frequency response need to be found. So this is, so let us because we want to find the frequency response of amplifier. So far we already saw this circuit diagram. So we could able to get an expression for the voltage gain of this amplifier as minus GM into RD. You might have seen that, okay, we have written a frequency, a small signal model of this particular type of amplifier. Of course, this R signal is one thing which is new compared to the previous one, and we could able to write this as R in, which is R1 parallel R2, and this was like gate, this is source, and you have a drain here, and you had a current source which was GM into VGS, where this was the small signal VGS, and this is V in, this is R1 parallel to R2, and we had the resistor RD, and this was V0. So whatever gain expression we got, we said that this is a midband gain. So this is a midband gain. So in this midband gain, we're not considering any capacitors. We are assuming that all capacitors are not considered. In the midband gain, this is the AC small signal model. But when it comes to frequency response, so we want to know the response of this circuit across all frequencies, starting from very low frequency, midband frequency, and high frequency. We have already obtained the midband frequency, how it looks like. But we need to find at low frequency and high frequency how does this circuit will respond. So we now consider all possible capacitances that are coming in this amplifier, in this MOSFET. So this MOSFET will have a capacitance which is CGD between gate and the drain. So this is a parasitic capacitance, and we're going to have a capacitance CGS. So now we will rewrite the small signal model of this amplifier by considering all resistors and capacitors without leaving out anything for all frequencies. So now let me consider this R signal here, and then let me still consider this CC. So this is my R1, this is R2, they are coming in parallel. This is R1, this is R2, and between gate and source, this is gate terminal, this is source terminal, I have a capacitance, this is CGS. sorry, let me write it as suffix cgs. Let me rewrite that. So this is cgs, and this is the gate, and I have this is gm into vgs. So this is rd, and here you just measure this is drain, and we know that we have this. So this capacitance is between gate and the drain, which is cgd. So this is rd, and this is grounded. This is cc, this is r signal. So this is vin. So this is the small signal model by considering all resistors and capacitors. Now let us rewrite this CGD, which is a floating capacitance in gate and drain, as a capacitance C1 here. I will replace this onto the gate side as C1, onto drain side it is C2 now. So now we will take out this. We are including the effect of CGD onto the gate side, onto the drain side using Miller's theorem. This is Miller's theorem. So using Miller's theorem, we could able to split this floating capacitance onto either side of the terminal. Now this is so and so. And of course, we know the expression for C1, C2. C1 is nothing but CGD multiplied by 1 plus 1. This is 1 plus AV. This is AV is the magnitude, and C2 is CGD into 1 plus 1 over AV. AV magnitude, because AV is usually equal to, this is minus GM into RD. So let us take, when I say AV magnitude, I need to take only GM RD as the value of that AV. So this is C1, C2. So now we can since these two are in parallel, I can write the entire capacitance as Cin, which is nothing but C1 plus CGS. So this is my input capacitance. At the output capacitance I have C2. So I can rewrite this entire small signal model into, I will just let me just put our signal here. So this is CC, and this is R signal, this is V in, so this is R in here, and this is C in, and this is gate, this is drain, this is source, and this is the dependent current source, which is GM into VGS, and I'll have a capacitance C2, which is also called as C out, output capacitance, and I have, this is my RD, this is V naught. So now, so this is by considering all capacitance and resistors, where Cin is given by CGS plus C1, where C1 is given by CGD, so on so. So that's what we have written here. This is C1, this is C2, C2 is C out. And what is Rin? Rin is R1 parallel R2. So let us rewrite this circuit diagram at low frequencies. At low frequencies, this effect will be more than our signal. So I will just at low frequency, how it looks is, so this is now replaced by, so now this is a capacitor. I will have this Rin, and I will have this. So this is at, this is your CC, this is Rin, and I will have, this is again, okay. When you're having two things among these two, you may have to select this at low frequencies and this at low frequencies. When it comes to high frequency, you'll be selecting this at high frequencies, this at high frequency, because at high frequency the reactance offered by this will be less, and this is during high frequency. So while writing, this is for low frequency. Let me write this. And of course on the other side, so there's no selection, because both will be because this RD and C2, which will be considered for whatever frequency, cutoff frequency comes out, that will be considered here. And this is V in. When you are considering at high frequency, so we will consider this. So this is actually a high pass filter, and this is including this is a low pass filter. Of course, this can be rewritten as something like this. This is minus plus, and you can write it as this resistor will come here, and this is your capacitor. This is RD, this is C out. So this is one low pass filter, low pass filter one. This is high pass filter one. So and then what you have at higher frequencies, you will have this R signal will be there, and this C in will be there. So this is C in, and of course you have this will be there whatever the frequency. So this is again at this is RD C2, this is V0. So you have another low pass filter. So actually what you have is one high pass filter, low pass filter 1, low pass filter 2. This cutoff frequency is 1 over 2 pi. If you can see, this is that low pass filter 1 over 2 pi Cc into Rin. This low pass filter 1, suppose if you call it as low pass filter 1, this is equal to 1 over 2 pi Rd into C out. Rd into C out. And this cutoff frequency of this filter will be 1 over 2 pi R signal into C, R signal into C. So you actually have three cutoff frequencies, one corresponding to low pass or high pass filter, and two more corresponding to the low pass filter. So I can rewrite this as something like this. So this is how the frequency response will look like. At lower frequencies, it acts like a high pass filter, and then it goes like this. So this is your first cutoff frequency, and then one more cutoff frequency. So suppose if you just take this as your 3 dB point, so if this is power P max, and at this point it is half of P max, half power point, and this is gain in dBs. So this will be like, okay, 3 dB, 0.32 difference. This is F1 and this is F2, and you have one more change in slope here. You can see the slope was like this and it has changed to this. So this is F3, and F1 is naturally the high pass filter 1. So this is equal to 1 over 2 pi R in into Cc. That's what is this. This is what is the one which is corresponding to high pass filter. This is one of the high pass filter. This is HPF, and you have this as one LPF, and this is the other LPF. Maybe this is 1, 2. This can be interchangeable. This can become 2. This can become 1. So depending on whose frequency is less, so these two are interchangeable depending on the value of R and C. And what is F2? It is 1 over 2 pi RD into C out. And what is F3? F3 is 1 over 2 pi R signal into C. So these are the cutoff frequencies, the frequency response of course this you can see this fairly constant. So this will be fairly constant in goes like this. So you can just rewrite. So this is fairly constant, comes down here and then again comes down. It's F1, F2, F3. Don't simply, okay, we have seen in the answer papers, you just randomly write it and do it like this. This is absolutely wrong. So you cannot write this. On this x-axis it is frequency, and y-axis it is gain in dBs. You have to write a flat curve at midband, and it should be, of course, this should be corresponding to a 3 dB point. So just write it 3 dB down here, one more 3 dB down. So this is F1, this is F2, this is F3. So this is what is the frequency response. Of course, maybe we have done many problems where the values of R1, R2, the capacitance and the gains are given. So you can able to easily find out what is the corresponding cutoff frequencies and the gain. So this is called as half power cutoff frequency, half power cutoff frequency. This is the bandwidth, and this is the second pole of this frequency response. After this, let us move on to how do we consider the current mirrors. So let us see how do we have a current mirror, because we have seen so many circuits where, so now if you want to get, assume that this is 1 milliampere. So this 1 milliampere need to be converted to either 0.5 milliampere or 2 milliampere. How do I do is, so this is the circuit what I'm looking at. Assume that this is what I'm trying to do it over here. This is VDD, and assume that this WL is 20 and this WL is 10. And if you want to find what is ID, this is, let me say it as M1, M2, this is ID2, this is some RD. So RD should be such that this should keep this MOSFET M2 in saturation region. So now the current that is flowing ID2 is nothing but W by L of 2. Let me call this as I reference. So ID2 is nothing but W by L of 2 divided by W by L of 1 multiplied by I reference. So since it is 20, since it is 10, and since it is 1 milliampere, so this is 2 milliamperes. Suppose if you have one more circuit where you have something like this here, this is again one more NMOS. Suppose if I take the same tapping and then connect it here, and if this RD is such that to keep it in saturation, if this W by L is 5, if this W by L of third transistor is 5, suppose if you want to find what is ID3, so ID3 is actually equal to 5, that is W by L of 3 divided by W by L of 1 multiplied by I reference. So now this will be 5 divided by 10 into 1 milliampere, which happens to be 0.5 milliampere. You can see this 1 milliampere can be mirrored to here as 2 milliampere, and it can be mirrored as 0.5 milliampere depending on the ratio of W by L of this transistor with respect to the reference transistor. And of course, you can just think of course, this is a conceptual thing. So how do they actually realize this? So they actually put a resistor. This resistor value will decide what is the current that is flowing. So instead of this, you can put a resistor of certain value, so that resistor will decide what is the current flowing through the circuit. Suppose if I do something like this now, so I will do this, and let me connect one more such. So simply just to give a practice to you people, how does the current will differ. Let me say it as some VB1. Let me say this as some VB2. Let me just take the tapping for this from this. Let me take it to this, and for this, let me take it from here. Let me have some V bias. Okay, assume that let me give some input voltage itself. So this is, you give some input voltage, give some input voltage. This is ground, this is VDD. So this is your PMOS transistor, this is again PMOS transistor, this is NMOS, this is NMOS. Assume that this is NMOS transistor. We can actually identify which is this amplifier is. Let me have this. Let me have this as a PMOS transistor. Let me have it as a NMOS transistor. Let me have it as this. Let me say this is V03, this is V01, so V02. As I said, okay, in the beginning, pause the video wherever you're not getting it and then try to understand what's happening. So we want to identify what are the currents flowing in different cases. Let us assume that this is 1 milliampere. I want to know what is ID1 here. I want to know what is ID2. I want to know what is ID3. I want to know what is ID4. So this is one amplifier. This is another amplifier. And this is the third amplifier. So let us try to identify the amplifiers also. Let us randomly take some magnitudes. So let this be W of this. Let this be 15. Let this be 25. Let this be 20. Let this be 40. Let this be 60. Let this be 5. Let this be 80. Let this be 65. So some random values I have taken. So let us try to find out what is ID1. So to find ID1, so this is the reference current. This is 1 milliampere multiplied by 15 by 10. 15 by 10. So whatever the current comes, this happens to be 1.5 milliampere. So ID1 is 1.5 milliampere. So then that becomes the reference current, and you can see now you have 1.5 milliampere. So now I want to find what is ID2. So what is ID2 now? For ID2, the reference current is this. So reference current is 1.5 milliampere multiplied by, this is 20 divided by 25. So of course you find the ratio of 20 divided by 25 into this ID1 is actually 1.5 milliampere. So since the reference for this is this, it is 20 divided by 25 into ID1. This is what is ID2. What is ID3? ID3 is actually this. For this, reference is coming from this. The reference is coming from this. So reference is actually 1 milliampere multiplied by, it is 60 divided by 10. See here, this is the reference what you have. This is a reference. So this is 1 milliampere and it is 60 by 1. It's actually 6 milliampere. 6 milliampere. So here it is. ID3 is 6 milliamperes. So for this, which is this, it is ID4. ID4 happens to be, which is a reference for this. Reference for this is this. So that means it is ID1. So what is ID1? It's actually 1.5. It is 1.5 into, this is 65. 65 divided by the reference of this is 25. So this is 25. So whatever the ratio that comes, so it's actually milliampere. So it is 1.5 milliampere into 65 by 25 is the current. Hope you got it. Maybe you can just pause it, rewind it, try to find out how I'm just writing all these things. And let us carefully identify the amplifiers. You can see this is the input is applied here, the output is taken here. So this is a CD amplifier. This is a CD amplifier with a load as R0. This is R0 load, and this is input is given here, output is taken here. So this is a CS amplifier. This is a CS amplifier, and here the input is given here to the PMOS transistor, output is taken here. This is also a CS amplifier. This is also a CS amplifier. So this is CD, CS, CS, and this is the current that are flowing in different things. So to find the gain, of course, you should know what is the WBL of all these things. You have to find the value of GM. So once you're fine with the GM, so you can find what is the expression or the values of gain of these amplifiers. So from a reference of 1 milliampere, ID1 is mirrored to as 1.5 milliampere, and ID2 will be 1.5 into 20 by 25, and ID3 is this. So for which the reference is coming from this, which is 1 milliampere into so and so. And for ID4, the current, the reference is this, which is actually ID1. ID1 happens to be 1.5 milliampere multiplied by 65 by 25. It's what is this. Okay, this is how you can able to easily find out the current using current mirrors. So current in different amplifiers using current mirror. Can you able to mirror the current of desired. So this completes the analysis of CS amplifier frequency response and the current mirror, which will going to provide sufficient current or desired current to different amplifier stages. Thank you. Next we'll meet in differential amplifiers.